Welcome friends. Let us today try to understand about the closed loop frequency response of control systems and how we can design a compensator or controller for a control system by studying the closed loop frequency response. So the major points we are going to discuss today are concept of closed loop frequency response, the basic need why you should go for closed loop frequency response study, then the closed loop transfer function, then the need for compensation and a simple or basic method of compensation. So friends, we start with the need of the closed loop control system and its frequency response. So a closed loop control system should be ideally a low pass filter, as we have discussed it many times, because a real system, when it is an electromechanical or electronic system, it has a natural tendency to respond to certain range of frequency, and it will show an attenuation in the output or the fall of gain beyond a certain frequency value. So far we have studied that there is a corner frequency on bandwidth, and below which there is a fall of the slope, which we have shown by negative slope in decibels per decade. So a closed loop negative feedback system is compensated by a controller or compensator to attenuate the most dominant root. Generally, the complex root pairs are creating the most dominant or most effective or most delayed response of the system. So we think of compensating the roots which are closer to the imaginary axis on the S plane. So whenever we speak about a control system and its Bode response, suppose for a second order system, as we have discussed earlier, we have, I'm drawing it again for your convenience. So we have a decibel scale for a second order system. So this is the magnitude equals to 20 decibels, 20 log base 10 of the gain, and this is in g omega, gj omega, and suppose we have the 0 decibel line. So initially we have a 0 decibel asymptote, and later for a second order system this is of minus 40 decibels per decade slope, because the gain is reducing after the corner frequency or the bandwidth. So this is the bandwidth, and this is the axis. You can take omega by omega n. This is on logarithmic scale, and for this I am assuming that here it is for damping ratio equals to 1 for a second order system, and for it is, if we want to consider the phase, so I'm trying to consider the phase in such a way that it is in degrees, phase in degrees, and this is from 0 to minus 90 through minus 180. So we have to see that the corner frequency is such that the tracing will have a slope of minus 90 degree at the corner frequency like this, then it will go like this. So here we see that for damping ratio 1 we have the corner is to be very smooth. So let us write down the points. First one is that closed loop control system should be low pass filter ideally, or low pass system ideally. So ideally low pass system. And the second point is that for a second order system, damping ratio 1 will show a smooth turn. I should write in bracket fall of gain in Bode plot near the bandwidth or corner frequency. So if you can recall, in the case of second order system with complex roots and underdamped case, if we reduce the damping ratio, so for a second order system with damping ratio equal to 0.1 will show an abrupt peak near the corner frequency called as resonant frequency. So we need to find out a way in which this resonant peak can be avoided. So fourth, a compensator, attenuator or controller needs to be designed to compensate the unwanted resonant peak. So our whole effort is to avoid the situation. So whenever there is a sharp fall of the gain after a frequency, around a frequency, or a sharp rise of gain, there is definitely going to be a sudden rise or dip of the gain, and this will cause a disturbance to the system which is unwanted. In the case of you are riding a bicycle or a bike or a car or an aeroplane, you will find that such frequency crossings will create a disturbance to the system that you can experience. So let us go a little further and find out the closed loop transfer function and see how it is useful for our purpose. So let us study the closed loop transfer function. what is this closed loop transfer function. So we start with the block diagram, where we can say that we have system representation by GS. Before this, we are placing a controller, which is basically remove the or compensate the unwanted things in the plant. So we'll see how it will happen. So let us design the control system, and for that we start by drawing the block diagram. So this is the block diagram for our design. So here you have ES, the error signal, this is plus, and the feedback signal. You can take unity feedback, or you can take the filter HS as per your convenience, but without loss of generosity you can use a unity feedback as well. So we can write from here the error signal ES, as we have already derived in the during the discussion on unit 1 on block diagram of control systems. So ES equals to RS minus HS, the signal from here. So HS into YS, HS into YS, then ES equal to ES equal to RS minus HS YS, where YS equal to RS minus YS. Sorry, this is YS equal to GS, directly coming from GS, YS equal to GS, and before that there is KS, and before that there is signal ES. So it should be written like this. So now we can write the ES equal to ES equal to RS minus HS into GS into KS into ES. Just I am replacing the value of YS in the first equation. So we have three terms, and terms common to ES can be taken on the left, and we can write, this is for single input single output system, we can write like this. So this 1 plus your HS GS KS, this will come together. So terms are on the left, so we keep the things on the left. ES on the right equals to RS. So let us go further. From this we can write ES equal to 1 divided by 1 plus HS GS KS, and that is multiplied by reference input. So by replacing the value of ES in YS, we get, in front there are GS and KS, so we get directly GS into KS divided by 1 plus HS GS KS into RS. So from here I can find a transfer function TS equal to YS divided by RS. This is equal to GS into KS divided by 1 plus hs, gs to ks. Now, as we have seen, the second order system transfer function is defined as for second order system transfer function is standard form is omega n square divided by s square plus 2 eta omega ns plus omega n square. So without any loss of genericity, when there is no controller and we have unity feedback, then Ts equal to Gs divided by 1 plus Gs, and this is equal to the situation which is equal to omega n square by s square by 2 eta omega ns plus omega n square. So if you try to find out Gs from this, what we are going to get, let us see. So from here we can use a theorem actually, that is A by B equals to A plus B by A minus B by A minus B. So this formula can be implemented on both the sides. So by using this we can write Gs plus 1 plus Gs divided by A minus B is Gs minus 1 minus Gs. This is equal to A plus B is 2 omega n square plus s square plus 2 eta omega ns divided by A minus B is omega n square minus s square minus 2 eta omega ns minus omega n square. So we have 2Gs plus 1 divided by minus 1 equal to 2 omega n square plus s square plus 2 eta omega ns divided by minus of s square plus 2 eta omega ns. So we have minus minus cancelled on both the sides, so we have 2G plus 1 equal to 2 omega n square plus s square plus 2 eta omega ns divided by s square plus 2 eta omega ns. So taking 1 to the right side, we get 2G equals to 2 omega n square plus square plus 2 eta omega ns. So when 1 is taken to the right side, so it will become here minus 1. So minus 1, when we take LCM of this, so minus 1 multiplied by s square plus 2 eta omega ns. So this is the numerator, and denominator is given by square plus 2 eta omega ns. So we can see that this portion are cancelled direct. So 2Gs equals to 2 omega n square divided by s square plus 2 eta omega ns, and which means that Gs equal to omega n square divided by, you can take s common, then we have s plus 2 eta omega n. once we got this, we understand that the GS, that is the open loop transfer function, is basically your transfer function with a constant in the numerator, and there are two poles at the denominator. These two poles are first the integrator, that is the pole at the origin, and second there is a pole to the left of the origin. So from this we can say that our system will be like this. You have the RS, which is fed to the system. GS, this is omega n square divided by S into S plus 2 eta omega n, and this output YS is actually taken as feedback, and this is the minus sign. So here I can see that we have the poles at S equal to 0 and S equal to minus 2 eta omega n. These two poles are there, and when the value of omega n varies from 1, this value is going towards 0.1. So we can understand that the Bode plot will show us a peak in its response. So we have a Bode plot with 0 decibel line, and the magnitude is in decibel, and here we can see that we have a second order system with a peak like this. So because of this peak is giving us omega r, that is the resonant frequency, and here we have mr, the resonant peak. So damping theta equals to 0.1. so this peak is unwanted, so we have to remove this peak from here. This should be removed, very much important in this case when the damping is less. So for this, the phase will be, this is your 0 degree line, degrees the phase, this is your minus 90 degree line, and this is your minus 180 degree line, minus 180 degree. So we will see that we will have a response like this when theta equal to 0.1. So this open loop transfer function, we generate an effect of resonant peak in the response as observed in the Bode plot. Thus we require a compensator or a controller that can compensate for the pole at origin, that is S equal to 0, and the pole at minus 2 eta omega n. So these two poles need to be compensated by a compensator, and we have to use the design in such a way that the compensator thus formed will generate a closed loop effect where the sharp fall of minus 40 decibel per decade, here you have minus 40 decibel per decade, this has to be eliminated. As I already mentioned in our previous lecture, that this fall should not be sharp, it should be gradual like this, minus 20, minus 40, like that. So how we can make it, how we can adopt this technique? For that, first I have to compensate for this pole at the origin, that is the integrator, and second and pole at minus 2 eta omega n. So I am trying to design a controller such a way that the controller case should be equal to, first I have to compensate for s equal to 0 of the plant. So I place a pole little on the left of the origin, so it can be like this, s plus 0.001. So a pole is placed little on the left of the origin, sorry, a 0 in the of the controller is to the left of the pole of the plant at the origin. So first factor will compensate for the pole at the origin, that is the integrator, and the second factor will compensate for s equal to minus 2 eta omega n. So here we will place a pole same as the value of this, so that the pole of the plant is compensated. Now I have to place two poles because I have compensated two poles from the plant, so I have to place two poles, s plus a and s plus b, in such a way that neither they are too much closer to the imaginary axis on the s plane, nor they are too much far. Means we are placing two poles at minus a and minus b such that the first pole will compensate for a 20 decibel per decade slope, that is minus 20 decibels per decade. So this will be the first pole at lower frequency, say A, and then we will have minus 40 decibel per decade, so that we can have at the second frequency B. So these two frequencies A and B can be designed in that way. So when you are placing the poles on the negative real axis, the first frequency which is obtained is A, and the second frequency which is obtained is B. So now when we are drawing the Bode plot for the system, how the system response is modified, let us look into it. So let us write down few important points here. First point is that thus the case, the controller case should compensate for integrator and the pole at s equal to minus 2 eta omega n. So we place a 0 slightly to the left of integrator. And one thing I tell you very clearly, that whenever we are designing a real system, suppose we are designing a controller using some electronic circuits, or you are designing a chip, the integrator which you are placing in your design, that should be little left to the imaginary axis, because no real integrator can be placed at the origin. We cannot place a pole at the origin in real design. This is not possible. So we have to place a pole little to the left of the imaginary axis. So then to compensate for the specifications of low pass system, we need to place two poles in the controller at different frequencies. So these are mid frequencies. So let us plot the bode once again so that we can compare the things in reality. So we have the system, and here is M magnitude in decibels. Then we have the 0 decibel line. Here the 0 decibel line is there, and we are plotting something. Let us change the color for clarification. So we are plotting at damping ratio equal to 0.1. so plot will be something like this. So this is minus 40 decibel per decade slope, and this is the MR, this is the MR, and we have damping ratio equal to 0.1, and for this the phase should be your, this is minus 90, this is 0, and this is minus 180 degree. So you have phase plot like this. So this is the line for your omega r. We have over here omega r, we have omega r over here. So here I can draw the plot like this, which is very stiff in the case of damping ratio eta equals to 0.1. Now over this I would like to overlap the design. So when I have the frequency A and frequency B like this around omega n, so my asymptote will go like this, will go at A like this, then it will fall by minus 20 decibels per decade up to B, then minus 40 decibels per decade like this. This is minus 20 dB per decade, this is minus 40 dB per decade. So for this the actual asymptote should be like this. So I take another color for clarity. So this is the actual asymptote. like this it will come. So similarly we will have a plot of phase. So you can draw the line up to here, and from here also you draw the line. So for phase you can draw in such a way that you get a little smoother slope, because first one will have from A to B we have minus 20 decibel per decade. So naturally for A to B you will drop like this. So A to B you have the drop of the slope like this, and from B further we will have a drop like this. So when I am trying to draw the phase plot, it should be like this actually. Sorry, it should be like this. It should be like this, then like this. For here also it should be like this, like this. So we'll have another phase plot pattern, which is the new phase plot pattern. So this is for compensated plant. Compensated plant. So we can see that the abrupt fall is not there, as well as the resonant peak is not there. So this has been removed. So that is how the design of a controller should be able to compensate the resonant peak of the system due to the presence of the complex underdamped root of low damping ratio. So with this we are through for the closed loop frequency response and the compensation of plant, and in the next lecture we will discuss about the minimum and non-minimum phase systems. So this is the textbook by Professor M. Gopal. I always suggest because of its simplicity, and quite a portion has been taken from this book. And the two reference books are by Professor Sanjay Mandal and Professor Said Hassan Said from Integral University Lucknow. So these two reference books can also be used. They are available in online also. If you find this lecture useful for you, please like the video, and those who could not subscribe, please subscribe it so that you can get the notification for the next video upload. Thank you for your patient listening.